Hello friends, welcome to my second lecture on duality. Now let us first discuss duality principle. If the primal and the dual problems have feasible solutions, then both have optimal solutions, and the optimal value of the primal objective function is equal to the optimal value of the dual objective function, that is maximum of z equal to minimum of w. This is the fundamental theorem of duality. It suggests that an optimal solution to the primal problem can directly be obtained from that of the dual problem and vice versa. Now let us discuss working rule to obtain an optimal solution to the primal problem from that of the dual problem. Suppose that we have already found an optimal solution to the dual problem by simplex method. Then the rule says if the primal variable corresponds to a slack starting variable in the dual problem, then its optimal value is directly given by the coefficient of the slack variable with changed sign in the Cj row of the optimal dual simplex table and vice versa. Now the rule 2, if the primal variable corresponds to an artificial variable in the dual problem, then its optimal value is directly given by the coefficient of the artificial variable with change sign in the Cj row of the optimal dual simplex table after deleting the constant m and vice versa. So, for example, let us consider the LPP minimized z equal to 0.7 x 1 plus 0.5 x 2 subject to x 1 greater than or equal to 4, x 2 greater than or equal to 6, x 1 plus 2 x 2 greater than or equal to 20, 2 x 1 plus x 2 greater than or equal to 18, x 1 x 2 greater than or equal to 0. So, we will write the dual of this problem first. So, dual of this problem will be maximize w, okay, because this is minimization problem. So, dual will be maximize w equal to 4 by 1 plus 6 by 2 plus 20 by 3 plus 18 by 4, okay, that is b 1 by 1, okay, b 1 by 1 plus b 2 by 2 plus b 3 by 3 plus b 4 by 4. Okay. So, 4 by 1 plus 6 by 2 plus 20 by 3 plus 18 by 4, okay. And then here the x 1 is greater than or equal to 4. So, the matrix is this 1 0, then 0 1 1 2, okay, 2 1, okay. Okay, we have the 4 constants x 1 x 2, x 1 greater than or equal to 4, x 2 greater than or equal to 6, x 1 plus 2 x 2 greater than or equal to 20 and 22 x 1 plus x 2 greater than or equal to 18. So, the left hand side of these constants is the result of the multiplication of the matrix 1 0 0 1 1 2 2 1 by the vector x 1 x 2. Okay. So, when we write the dual, okay, then we take the transpose of this matrix. Okay. So, transpose of this matrix will be 1 0 1 2, okay, 0 1 2 1, okay. This is transpose of this matrix. Okay. So, this into by 1 by 2 by 3 by 4. Okay. And then greater than or equal to will be converted will be changed to less than or equal to. Okay. So, we will have, so the left hand side of the constants will be then this will be equal to by 1 plus 0 by 2 plus by 3 plus 2 by 4. Okay. And the second row will be 0 by 1 plus by 2 plus 2 by 3 plus by 4. Okay. So, by 1 plus 0 by 2 plus by 3 plus 2 by 4 will be less than or equal to C 1. Okay. So, by we will have the constant by 1 plus 0 by 2 plus by 3 plus 2 by 4 less than or equal to C 1, that is 0.7, and the second one will be 0 by 1 plus by 2 plus 2 by 3 plus by 4 less than or equal to C 2, that is 0.5. Okay. So, the dual of this problem will be maximize W equal to 4 by 1 plus 6 by 2 plus 20 by 3 plus 18 by 4 subject to the constants by 1 plus 0 by 2 plus by 3 plus 2 by 4 less than or equal to 0.7 and 0 by 1 plus by 2 plus 2 by 3 plus by 4 less than or equal to 0.5. Okay. So, this is our dual problem where by 1 by 2 by 3 by 4 are greater than or equal to 0. Okay. So, we have this maximum of W 4 by 1 plus 6 by 2 plus 20 by 3 plus 18 by 4 subject to by 1 plus by 3. Okay. This by 1 plus by 3 plus 2 by 4 less than or equal to 0.7 by 2 plus 2 by 3 by 2 plus 2 by 3 plus by 4 less than or equal to 0.5. Okay, by 1 by 2 by 3 by 4 greater than or equal to 0. Now, let us express this problem in the standard form. So, here we have the constants of the type less than or equal to. So, we will use slack variables. Okay. And when we use slack variables, there are two constants of less than or equal to type. So, we will need two slack variables S1 S2. So, objective function will be written as W equal to 4 by 1 plus 6 by 2 plus 20 by 3 plus 18 by 4 0 into S1 0 into S2 subject to these equations will be these constants will be converted into equations by means of S1 S2. So, by 1 plus 0 by 2 plus by 3 plus 2 by 4 plus S1 plus 0 into S2 equal to 0.7 and then 0 into by 1 plus by 2 plus 2 by 3 plus by 4 plus 0 into S1 plus S2 equal to 0.5 by 1 by 2 by 3 by 4 greater than or equal to 0. So, now our problem dual problem has been expressed in the standard form. Now, let us find an initial basic feasible solution. So, setting now there are two equations. Okay. This equation and this equation, there are two equations and there are 6 variables. So, we can take any 4 variables equal to 0. So, let us take by 1 by 2 by 3 by 4 equal to 0 and then we get the value of S1 equal to 0.7, S2 equal to 0.5. So, we get taking non basic variables as by 1 by 2 by 3 by 4 each equal to 0. The basic solution is by 1 by 2 by 3 by 4 equal to 0 non basic and S1 equal to 0.7, S2 equal to 0.5 basic variables. So, since the basic variables are greater than 0, the initial basic solution is feasible and non-degenerate. Okay. Now, initial simplex table is as follows. So, this is initial simplex table. C0, okay, this small C0 contains the coefficients of the variables by 1 by 2 by 3 by 4 S1 S2 which are 4 6 20 18 0 0 and basic variables are S1 and S2. Their coefficients in the objective function are 0 0. So, that constitute the CB column. Okay. And the body matrix is this is the body matrix. So, 1 0 1 2 and then 0 1 2 4, that is body matrix. So, we have this body matrix 1 0 1 2 0 1 2 1, okay, and the unit matrix is 1 0 0 1. Okay. Now, let us calculate, let us solve this by using simplex method. So, we find Zj equal to sigma Cb Aij. So, 0 into 1 is 0, 0 into 0 is 0. So, Zj is 0 for j equal to 1 and then 0 into 0 is 0, 0 into 1 is 0. So, again we get Z2 equal to 0 and then 0 into 1 is 0, 0 into 2 is 0. So, we get 0, here also we get 0, here 0, here 0. Okay. Now, 4 minus 0 is C1. So, that is 4, 6 minus 0 is 6, 20 minus 0 is 20, 18 minus 0 is 18, then 0 minus 0 is 0, 0 minus 0 is 0. Now, let us see Cj is positive, okay, in some columns 1, 2, 3, 4, in 4 columns Cj is positive. So, let us find the maximum value of Cj. Maximum value of Cj is 20. So, this is our key column. Then we find the ratios, okay. of the B values in the B column by the values in the corresponding values in the key column. So, 0.7 divided by 1, okay, 0.5 divided by 2, and this is 0.7, this is 0.25. So, of the two positive values 0.7 and 0.25, 0.25 is minimum. So, this row is our key row. Okay. So, this row is our key row. At the intersection of key row and the key column, we have the key element. Key element is 2. Okay. So, S2 is outgoing variable, Y3 is incoming variable. So, Y3 incoming variable, and S2 is outgoing variable. So, in the next simplex table, S2 will be replaced by 3. So, by 3 is the incoming variable and S2 is outgoing variable. So, in the next simplex table, we will have basis as S1, S2 will be replaced by 3, and CB column will have coefficient of S1 in the objective function is 0, coefficient of Y3 in the objective function is 20. Okay. Then we have Y1, Y2, Y3, Y4. Okay. So, they are 1, 0. Okay. So, before that, let us now divide the key row elements by the key element. So, we have 0, okay, 1 by 2. Okay, we are dividing by 2 the key row elements. So, then we have by 3 as 1 and then 1 by 2, that is by 4. So, then S1 is 0, S2 is 1 by 2, okay, and B becomes 0.5 by 2, that is 0.25. Okay. So, that is B. Okay. Now, with the help of this element 1, okay, we make this element equal to 0. So, we subtract this row, okay, the new key row after we have got it divided by 2, okay, this row we subtract from the first row. Okay. So, 1 minus 0 is 1, okay, then 0 minus half. So, we get minus half. Okay. Then by 3 this becomes 1 minus 1 0, by 4 this is 2 here and here we have 0. So, we get 2. Okay. And then S1 is 1 minus 0. So, we get 1. S2 is 0 minus half. So, we get minus half, and then 0.7 minus 0.25, okay, 0.7 minus 0.25. So, we get 0.45. So, this is 0.45. Okay. So, let us see the next simplex table, 1 minus half 0. So, 1 minus half 0, then we have this will be 3 by 2, 2 minus half 3 by 2, okay, and here we have 0. So, this will become 1, okay, and then S2 will become minus half, correct. Okay. So, we have first row is 1 minus half 0 3 by 2, 1 minus half 0 3 by 2, 1 minus half 0.45, 0.545 is 9 by 20, okay, and the second row is 0 half 1 half, 0 half 1 half, 0 half 0.25, 0 half 0.25. Okay. So, this is our new rows. Now, we will find the value of Zj. Okay. So, 0 into 1 is 0, 20 into 0 0. So, we get 0, 4 minus 0 is 4, then we get 0 into minus half 0, 20 into half is 10. So, we get total 10, and then 0 into 0 is 0, 20 into 1 is 20. So, we get 20 here, then 0 into 3 by 2 is 0, 20 into half is 10. So, we get 10 here, 0 into 1, 0 into 20. So, 0 here, then 0 into minus half, 20 into half. So, we get 10 here, and 0 into 9 by 20 is 0, 20 into 1 by 5, 1 by 4. So, that is 1 5 we get. Okay. Now, this is 4, this is 6 minus 10 is minus 4, 20 minus 20 is 0, 18 minus 10 is minus 18 minus 10 is 8, then 0 minus 0 is 0, 0 minus 10 is minus 10. Okay. So, there are again GCJ is positive in some columns. In this column Cj is 4, in this column Cj is 8. Okay. So, we take the maximum value. So, 8 is the maximum of the two, 4 and 8, and therefore, this is our key column. So, this is key column. Now, divide the values of in the V column by the values in the key column. Okay. So, 9 by 20 divided by 3 by 2. So, that means 2 by 3. So, we get 3 by 10 this value. Okay. And then 1 by 4 divided by 1 by 2. So, we get 1 by 2. Okay. Now, out of the two positive values of theta, 3 by 10 and half, this is 0.5, this is 0.3. Okay. So, 0.3 is the minimum, and therefore, this is our key row. Okay. So, at the intersection of key row and key column, we have 3 by 2. So, key element is 3 by 2. Okay. Now, this by 4 is incoming variable, S1 is outgoing variable. So, by 4 is incoming variable and S1 is outgoing variable. So, in the next simplex table we shall have CB, in the CB column we shall have here the coefficient of by 4, coefficient of by 4 means 18. Okay. Then we have 20, and in basis we will have S1 is replaced by 4. So, by 4 here, and here we have y 3. And then this row, okay, key row elements are divided by key element, that is 3 by 2. So, we will have 2 by 3, okay, 3 by 2 1 is divided by 3 by 2 gives 2 by 3, and then minus half into 2 by 3. So, 2 will cancel, we get minus 1 by 3. Okay. Then 0 divided by 3 by 2 is 0, 3 by 2 divided by 3 by 2 is 1, and then 1 divided by 3 by 2 is 2 by 3, okay, minus half divided by 3 by 2. So, minus half into 2 by 3. So, minus 1 by 3, okay, and then 9 by 20 divided by 3 by 2. So, we get 9 by 20 into 2 by 3, that is 3 by 10. So, we get here 3 by 10. So, this is by 1, by 2, by 3, by 4, and then S1, S2 and B. Okay. And now, with the help of this 1, okay, we make this entry 0, okay, in the key column. Okay. So, we multiplied by half and subtract from this row. Okay. So, we multiplied by half, when you multiply it becomes 1 by 3, 1 by 3 we subtract from 0. So, we get minus 1 by 3, and then we have here we are multiplying by 1 by 2. Okay. 1 by 2 when we multiply here we get minus 1 by 6, and after that we subtract. Okay. So, 1 by 2 plus 1 by 6 we have. Then here we have 0 is multiplied by half and then subtracted from 1. So, it will remain 1. Okay. Then this will become 0, and this will become we are multiplying this by 1 by 2. So, it will become 1 by 3. 1 by 3 we subtract from 0. So, we get minus 1 by 3. We are multiplying by half and then subtracting. So, this is minus 1 by 6, we are subtracting it. So, what we get in the S2 column? S2 column is 1 by 2. So, 1 by 2 plus 1 by 6 we have, and here we get 1 by 4. We are multiplying it by half and subtracting. So, minus 3 by 10 into 1 by 2. Okay. So, what we shall have? 1 by 2 plus 1 by 6 is equal to 3 plus 1 divided by 6. Okay. So, that is 4 by 6, this is 2 by 3. Okay. And so, 1 by 2 plus 1 by 6, 2 by 3, this is 2 by 3, and then we get 1 by 4 minus 3 by 20. Okay. 3 by 20. So, we get 20 here. So, 5 minus 3. So, we get 2 by 20. So, we get 1 by 10. So, this is 1 by 10. Okay. So, first row, okay, let us see, first row is 2 by 3 minus 1 by 3 0, 2 by 3 minus 1 by 3 0, then we have 1 2 by 3 minus 1 by 3, 1 2 by 3 minus 1 by 3, 3 by 10. Okay. Second row is minus 1 by 3, then 2 by 3. So, minus 1 by 3, then 2 by 3, then 1 0. So, we get 1 0, and then minus 1 by 3, minus 1 by 3, then we have this one is 2 by 3. Okay. So, we get 2 by 3 here, and this becomes 1 by 10. Okay. So, we get 1 by 10 here. Okay. Now, let us find Zj value. So, Zj value comes out to be 18 into 2 by 3. So, that means 18 into 2 by 3 means 12. So, this when you multiply 18 to 2 by 3 you get 12, and you multiply 20 to minus 1 by 3. So, 20 into 1 by 3. So, this is minus 20 by 3. So, let us make a total of this. So, 12 minus 20 by 3 is equal to minus 20 by 3. Okay. So, this is 16 by 3. So, we get 16 by 3 here. Similarly, here Zj is 22 by 3, here 20, here 18, here 16 by 3, here 22 by 3, and here when we multiply 18 to 3 by 10, 18 into 3 by 10 plus 20 into 1 by 10. So, we get 54 plus 20, 74 by 10. So, this is 74 by 10. Now, let us find capital Cj. So, 4 minus 16 by 3 is minus 4 by 3, and 6 minus 22 by 3 is minus 4 by 3, 20 minus 20 is 0, 18 minus 18 is 0, 0 minus 16 by 3 is minus 16 by 3, 0 minus 22 by 3 is minus 22 by 3. So, we can see that Cj is less than or equal to 0 for all j. Okay. And so, Bi is greater than or equal to 0, B1 is greater than is equal to 3 by 10, B2 is equal to 1 by 10. So, I equal to 1 comma 2. Okay. So, Bi is greater than or equal to 0 for I equal to 1 comma 2, and therefore, since all Gj is less than or equal to 0, this gives the optimal solution, and the optimal basic solution is then by 1 equal to 0. Okay. So, by 1 equal to 0, by 2 equal to 0, by 3 equal to 3 by 10. Okay. By 3 we get as 3 by 10, and by 4 we get as by 3 we get as 1 by 10, by 3 we get as 1 by 10, and by 4 we get as 3 by 10, and by 1 by 2 equal to 0, and maximum value of Z is 74 by 10, that is 7.4, which is minimum value of this maximum value of we are using W. Okay. So, maximum value of W is 7.4, okay, which is equal to minimum value of Z. So, minimum value of Z is 7.4. So, we get this. Okay. Maximum value of W is 7.4. So, minimum value of W is 7.4, and we let us go to the rule. Rule says that the primal variables x1 x2 here correspond to the slack starting dual variables s1 s2 respectively. Okay. You can see here s1 s2. So, x1 x2 corresponds to s1 s2 here, and therefore, in the final simplex table of the dual problem, Cj values corresponding to s1 s2 are Cj values corresponding to s1 s2 are minus 16 by 3, minus 22 by 3. Okay. So, by rule 1, this is the rule, this is the rule. Okay. By rule 1, okay, if the primal variable corresponds to a select starting variable in the dual problem, then its optimal value is directly given by the coefficient of the select variable with changed sign in the Cj row of the optimal dual simplex table, and vice versa. So, we will change their sign to get the corresponding values for x1 x2. So, here this is Cj is minus 16 by 3 for S1, and for S2 it is minus 22 by 3. So, corresponding to them the values of x1 x2 are 16 by 3 and 22 by 3. So, x1 is 16 by 3, x2 is 22 by 3, and minimum value of Z is 7.4. So, this is the optimal basic feasible solution to the given primal in this case. So, we have discussed the how to solve the given LPP by converting it into the dual problem, and we solve it there and then determine the solution of the given problem. So, we have seen that by writing the dual of the given problem and solving it by the simplex method, we can determine the solution of the given primal problem. So, that is all in this lecture. Thank you very much for your attention.